This is the second program in our series on atomic theory. In particular, today we're going to take a look at the work of Niels Bohr and how the electrons are arranged within the atom. The first thing we need to understand about Bohr's work is the nature of the electromagnetic spectrum. We're all familiar with the colors of the rainbow: red, orange, yellow, green, blue, and violet. They're part of the visible spectrum of light, but it exceeds far beyond that. Before the red, we have the infrared and radio waves, and then after the violet, we have the ultraviolet and X-rays, all part of the electromagnetic spectrum. One thing these all have in common is they travel at the speed of light, c in this equation, 3 times 10 to the 8th meters per second. And they all follow what's called the universal wave equation, where the velocity of the wave is equal to its frequency times its wavelength. The wavelength of a wave is the distance between its crests. Here we can briefly compare X-rays at one end to TV and radio waves at the other end. TV and radio waves have long wavelengths, and X-rays much shorter wavelengths. The frequency of a wave is related to its energy. The greater the frequency, the greater the energy. So we can see that wavelength and energy are essentially inversely related. As one makes the wavelength longer, as in the case of infrared and radio waves, its energy is decreased. When I move to X-rays and ultraviolet light, they have more energy and shorter wavelengths. Spectra. I'm going to take briefly a look at 3 types of spectra. I'll begin with what many of us are familiar with. If we pass white light through a prism, we can break it down into its component colors: red, orange, yellow, green, blue, and violet. They all blend one into another in a continuous spread of color. If I make a change to this setup, replacing the white light with, say, a gaseous element at a high energy state, I can produce what's called an emission or a line spectrum. So my high energy gas contains one simple gas usually in it. That gas can be excited by either heat or passing electricity through it. And it produces discrete bands of color. These bands of color originate when the atom moves from a high energy state to a low energy state. If I combine these two ideas together and I shine white light through a low energy sample of the gas, I'll produce what's called an absorption spectrum. Now, if the gas is the same as that used in my emission spectrum, you'll notice that the colors and the dark bands complement each other, meaning they fit together. An absorption spectrum is created when energy is absorbed from white light to promote an element from a low energy state to a higher energy state. Niels Bohr work primarily focused around the use of an emission spectrum, and in particular the emission spectrum of hydrogen gas. So he used hydrogen under low pressure and passed electricity through it. That light was then broken into its component visible colors that we see here: the red, cyan, blue, and violet colors. Bohr came up with a few ideas concerning the spectrum. First off, he believed that the electron could only exist at certain discrete intervals of energy and not in between. So the electron either existed on the first energy level, the second energy level, perhaps the third energy level. It didn't exist at any point in between those. As the energy levels moved further out from the atom, they converged or got closer together. This was evident from looking at the spectrum. We can see as we move to higher energy levels, the blue light and the violet light, we can see that they start to get closer together. He interpreted the various colors as the electron transitioning from one orbit to another. So, for instance, the production of the red light. What he believed happened in this particular case was the electron moved from the third orbit to the second orbit. And in that transition, energy was released in the form of red light. If the electron was in the third orbit and then transitioned or disappeared and reappeared on the second orbit, it produced the cyan color. And similarly, to produce the blue color, a transition from the fifth energy level to the second energy level. Other transitions would be possible. The electron could move from the second to the first, or the fifth to the first, but those were all bands of colors that were beyond the visible spectrum. They would perhaps lie in the ultraviolet end of the spectrum that we couldn't detect. And similarly, there could be very small transitions, perhaps from the fourth energy level to the third energy level, the sixth energy level to the fifth energy level. That would be in the infrared region of the spectrum. Later work also suggested that the electrons existed in these orbits, but there were certain maximum numbers of electrons that could exist in each orbit. It's governed by the equation 2n squared, where n is the electron energy level. So at the first energy level, we can essentially have 2 electrons. At the second energy level, n squared becomes 4 times 2 gives us 8 electrons. And the third energy level can hold 18, and so forth. You might recall that our earlier model of the atom, that of Ernst Rutherford, was called the beehive model, where we had essentially the nucleus with the electrons moving around like bees. We can now move that model to that of Bohr, where the electrons exist on discrete orbits and not in between, and those energy levels get closer together the further out we move. So for instance, in earlier studies of chemistry, you might have recalled things that are called the electron arrangement of an atom, whereby we would say that in the case of lithium, which has 3 electrons, 2 of those electrons would exist on the first orbit and 1 in the second orbit. Now this isn't the end of how the electrons are arranged. We still have one more model to go, that of the quantum mechanical model of the atom. That'll be in the next program. Thanks for watching.